we are privileged and honored to have three amazing speakers. First, Dr. Emil Dimanchev, who is a postdoc at the Zero Lab at Princeton. And then Dr. Nora Hennessy. She is an assistant professor at the School of Sustainability at Arizona State University. And finally, Dr. Anirudh Subramanyam, who is an assistant professor at Penn State University. So today they'll be talking to us and presenting. So please give them your attention. We'll start with Dr. Emil Dimanchev. Thank you.
All right, thanks. I think you can now see my slides. So yeah, thanks for the invitation. I want to thank the Macro Energy Systems Fellows for coordinating this, especially Carla and Melik. Today, what I'll do is present recent work from two sets of projects that revolve around this central theme that motivates a lot of my work, which is how do we decarbonize energy systems when there are political constraints that might prevent us from implementing the optimal solution that we would like to implement? And also when there might be market inefficiencies or failures that mean that markets themselves are not operating optimally, and how that might change our planning decisions and optimal policy choices. Very broadly, my research is motivated by three kinds of questions. First, about how should energy systems be designed, or where do we want to go? Secondly, how should policies be designed and chosen? Or in other words, how do we get to where we want to go? What are the effects of alternative policy choices? And finally, how do we know? Um, and what kind of methodologies can help us answer these kinds of questions? My particular focus is on capacity expansion optimization-based methods. A little bit more specifically, what I am aiming to contribute to the macro energy systems field is investigating and improving the structural uncertainty, understanding of structural uncertainty, and improving the structural assumptions that we make inside of our models. So I bring operations research and economics into energy system optimization models to improve the mathematical representation of how, for example, decisions are made under uncertainty, how decisions are made under political constraints, and what that might mean for optimal policy and planning. And recently as well, how does endogenous learning impact or should impact optimal planning and policy choices? So you can think of me as a structural uncertainty person. Today, I'll talk about two sets of projects. First, one focused on the question of political constraints and how they impact climate policy choices. And secondly, a set of projects that I'm working on now as well in my postdoc at the Zero Lab on capacity expansion in electricity markets, specifically markets that are subject to inefficiencies in how investment decisions are made. So first, I would like to talk about a paper that we co-authored together with Chris Knittel at MIT back in 2023. This was really motivated by my time before academia advising on the European carbon pricing system, and noticing that even in a jurisdiction that was dedicated to making carbon pricing a centerpiece of its climate policy, there were very binding political constraints. And so Chris and I asked, to what extent can policy mixes or portfolios of different policies allow us to meet climate targets within political constraints? The general premise for this work is that policymakers have a choice between different instruments or policies to reduce emissions. On the right, they can reduce emissions using CO2 pricing, which is the economist first best optimal preferred policy, of course, but which is not very politically feasible. And on the left, there are all kinds of tradable performance standards or clean energy standards, renewable portfolio standards that we typically think of as more politically tractable, but that might come with trade-offs. There are different ways to define this decision space. We think, for example, of the standard percentage, or what percentage of clean energy, for example, um, is part of the total generation mix in the energy system. Or we can also define it as what percentage of emission reductions comes from any policy. So for the same amount of emissions being reduced, how much are we reducing emissions with CO2 pricing and how much with standards? So this question, which policy to use and crucially where to be on the spectrum, is being asked by policymakers pretty much everywhere. Um, but there are many criteria that might go into deciding where on that spectrum to be. But we notice that that debate is dominated, or has been dominated, by economics considerations of which one costs more or less. And from economic research, we know that CO2 pricing generally costs a lot less than standards to reduce the same amount of emissions. But with Chris, we asked about what the space in between looks like. In other words, what is the nature of this curve? Is it convex like this, or is it affine or linear, or is it concave? And so we used a abstract general analytical model, and we also used energy system models to answer this question. And we found that this is what the curve looks like. There are advantages to using carbon pricing, but those advantages diminish the closer we get to the theoretical optimal. So zooming out a little bit before I show you some specific results, but the overall takeaway to think about here is that essentially there is a near optimal space here that is close to the theoretically optimal policy of just using a carbon price. But there's a space of combinations of carbon pricing and standards that are close to optimal, but that we would expect to be much more politically feasible. And this, for example, might be one plausible explanation why we see combinations of these policies in the real world too. And what we're showing here is that these kinds of combinations make sense economically as well. We tested this numerically, as I mentioned, with energy system models. In one case, we used a computable general equilibrium model, the EPA model, and we tested this spectrum of policy choices, which on this figure, for example, on the first x-axis, you can see the percent abatement coming from carbon pricing from 0 to 100. Inversely, at this point here, we have 100% of abatement being driven by a standard and moving down to 0. And on the y-axis, we have policy cost. And so what we see is that the shape of this curve is generally convex. And if we focus on the clean energy standard policy, what we find is that if doing 100% carbon pricing here on the right reduces costs by 75% compared to using a standard to reduce the same amount of emissions. If we combine both policies and we use them to each deliver 50% of the emission reductions, we are already 65% more efficient. So in other words, partial reliance on carbon pricing delivers most of the benefits of the theoretically optimal carbon price. We also run GenX, the capacity expansion model developed by Jesse Jenkins and Esther Sepulveda, that we use also in the Zero Lab. And we find a very similar result when we compare renewable portfolio standard and carbon pricing. Once again, most of the benefits of cost efficiency that the first best pricing policy delivers can be found with a near optimal policy mix. So to concluding on this on this research direction, in general, the takeaway that we take from this is that there exists a near optimal climate policy mix or mixes that can meet emission reduction goals relatively cost effectively, but also deliver on other criteria such as political feasibility and many other goals and many other reasons for which we use standards and subsidies to reduce emissions. Secondly, if we stopped, okay, all right, we're good.
Thank you. Sorry about that.
Um, so oftentimes there is a counter argument to using standards saying that they will increase the cost of climate policy, but what we show is that partial reliance on standards actually comes at a relatively small cost. At the same time, this research has a very positive message for carbon pricing advocates because it shows that if you don't have any carbon price at all, even a small carbon price lowers costs very significantly. So when you are at the far end of that curve. Um, in terms of next steps that we're taking in this area, what I find really interesting is the potential to use bi-level optimization to explicitly model how a policymaker would make climate policy choices under political constraints. And in some work that we've already done on this, that there's a preprint for already out, we find that when policymakers use subsidies to decarbonize as opposed to a carbon price, the pathway for example, the capacity mix or the energy system can look very different from a pathway that we would model in the usual approach where we simply have an energy system model and we implement a carbon price or we implement an emissions constraint that represents a carbon price effectively. Great. So moving on to the second set of research, which is on capacity expansion in electricity markets. In electricity markets, there are growing concerns that investors as well as consumers are exposed to inefficient levels of risk. In theory, an investor in generation or storage should be able to sign a long-term contract with the consumer to hedge the risk that comes from volatile spot prices. And similarly, consumers that are worried about high electricity costs or scenarios with high electricity costs should be able to sign long-term contracts to hedge themselves against that risk. In practice, what we see in electricity markets is that this kind of contracting is fairly limited. PPAs, power purchase agreements that are being signed are almost exclusively being signed by big tech companies. And so there's a concern that as renewable adoption grows beyond big tech demand, we might see more and more risk being borne by investors, which I think we're already observing in the way that PPAs are becoming shorter and shorter. That was all summarized by Paul Josko recently, who said that when we liberalized electricity markets, we expected there to be a fair amount of contracting between investors and consumers, but we've seen less contracting than we actually expected. Overall, energy economists call this problem the missing market problem, which is essentially saying that in electricity markets, in reality, there is limited amount of contracting that happens, which exposes investors and consumers to uninsured risk. There are many reasons for this, including moral hazard problems and the fact that when consumers face very high costs for electricity, for example, because of an energy crisis, those costs are often socialized. And so there's a moral hazard that disincentivizes consumers from signing long-term contracts. There's also a reliability externality that we talk about in electricity markets. But given that in electricity markets, there is a lot of risk being faced by investors and consumers, how does that affect outcomes in markets? In general, we can think of markets as comprising three types of agents. And so this mental model that I'm showing you now really represents a framework that we're using to design and build new kinds of capacity expansion models for electricity markets. And we've already, and I'll show you some results from this modeling. Just very briefly, the three kinds of agents we are modeling are risk-averse investors who are maximizing profit, economic dispatch being performed in the usual way that we're familiar with, and risk-averse consumers who, given what they expect from the economic dispatch, might want to sign long-term contracts. This is not an arbitrary framework. This is what we do when we model capacity expansion. If we had a model that was stochastic and was representing risk, we would have exactly this picture, except that because it's a cost minimization central planner model, the implicit assumption it has is that this contracting is what we would call complete or ideal, which is not the case in reality. So we are building new kinds of models where we are solving each of these optimization problems separately and the equilibrium between them together. So in practice, this is an equilibrium problem that is very hard to solve. In my PhD, I took first steps toward making such models tractable to solve for systems with renewables and storage. And in this paper that I published with Stephen Gabriel, Lena Reichenberg at Chalmers, and Magnus Korpas at NTNU in Norway, we just tried to build intuition about how does this missing market problem affect the capacity mix in power systems. This shows the general result where we modeled New England, and in our main case, what we saw in the capacity mix is that when we move from a world where markets are optimal to a world that's a little bit more in the direction of being more realistic, we see that when there are no long-term contracts, there is more gas on the system, less renewables, and also less storage, which I think we saw for the first time with that paper. So storage and renewables are in a sense disadvantaged in a world where there's uninsured risk and contracting is incomplete. You might say that well, we would expect renewables to be disadvantaged when there is risk in the market, and and um, I would agree, but in the what we showed in the paper is that the reason why this happens is not what we actually expected. People usually think that renewables are sensitive to uninsured risk because they're more capital intensive, which is true, but the actual reason why we see a lot less investment in renewables, as we showed in the paper, is that they're a lot less able to pass on to consumers the higher cost caused by the risk premium that they have. And out of consideration for time, I'll leave that for questions if there are any, but happy to discuss further. In my current work, in my postdoc, what we're trying to do, to give you a brief overview, is to ask how does this problem materialize in real world electricity markets. And so we built a new kind of capacity expansion model for electricity markets where we're modeling this equilibrium problem, but we are introducing new decomposition algorithms and parallelization that allows us to solve this problem for very large scale studies. We are currently modeling the Texas system, for example, at a relatively high resolution in a problem that has over 900 million variables. For example, with 700 scenarios, and each scenario has thousands of operational hours, et cetera. And just to briefly tease that work, what we find when we compare now capacity mixes in different worlds where we have different amount of contracting, what we see is that relative to the optimal case, which is on the right, cases that represent more or less what markets are doing today. For example, this case with what we call a call option represents more or less an ideal capacity market. We see that in markets with ideal capacity markets, there's a lot less renewables than the amount there would be if markets were optimal. This has important implications for emissions because if we look at the emission outcomes, which is on the y-axis in this case with capacity markets, so the optimal case, we find that capacity markets should be expected to result in a lot higher emissions because they bias against renewables. So to briefly conclude, electricity markets, according to this work, are not fit for purpose, especially in highly renewable systems. The reason for this is not because short-term spot prices do not work when we have zero marginal cost for renewables, but the reason is because long-term markets are incomplete, and that biases the mix against renewables and storage. So we should be thinking more and working more on designing better long-term markets with perhaps mandatory contracting or centralized procurement that can address these challenges and better allocate risk and allow investors and consumers to hedge their risks. Very briefly, if you'd like to talk further about these topics, my email is on the top right, and the Zero Lab works on a broad array of subjects in these areas and beyond that I don't have time to cover, but you should check out the work of my colleagues as well on pushing the boundaries of energy system modeling and decision making under uncertainty, and improving planning and policy decisions. So with that, thanks. And I might not have left time for questions, so that's on me.
Thank you, Emil. That was amazing. Maybe we can leave questions to the end when the other two speakers finish, just to make sure that we allocate time for everyone. Now I'm excited to introduce Dr. Nora Hennessy from Arizona State University. And Dr. Hennessy, if you can go ahead and share your screen. Perfect.
All right.
Take it away.
Great. Yeah, thanks so much for having me today. I'm going to talk about something very different from the last talk. So I guess just to introduce my work more broadly, quickly, before I dive into this topic, I do a lot of work on energy systems decarbonization and how that interfaces with equity and environmental justice. But increasingly, as I have been doing this energy systems decarbonization work, I have kept coming up against sort of this idea that as we are, designing more cleaner, more decarbonized energy systems, more equitable systems, we also need to be cognizant that we are designing these systems in a world where the climate is already changing. And so we need to understand how our energy systems fit in to the climate that we're seeing and how vulnerable they are to climate hazards that we're already seeing. And so today I'm going to talk about a study that's focused on understanding the vulnerability of electric utilities in California to wildfires and post-fire debris flows. This was a study that I worked on during my postdoc with Mike Chester, and it came out about a year ago, and I'm happy to share the link in the chat at the end. But yeah, for now, I will just dive right into it. So, as many of you probably know, we are seeing an increase in wildfires throughout much of the Western United States, in particular California. So, by all sorts of metrics, we're seeing annual burn area increasing, we're seeing fire intensity increasing. And so, essentially, wildfire is something that California and the West has always dealt with, but it is becoming sort of an increasingly important threat that we need to be thinking about when we are thinking about our energy systems and our infrastructure more broadly. And so wildfires can directly damage infrastructure, through burning different assets, but they can also lead to secondary impacts. And so one of those important secondary impacts is post-fire debris flows. And so post-fire debris flows, for those of you who aren't familiar, are essentially what happens when you have rainfall over recently burned soil. And so when you have high intensity wildfires, they can change the chemistry of the soil. So the soil becomes more hydrophobic, so you get increased runoff. And this can lead to debris flows. Sometimes you might hear them called mud flows. You might remember in the Los Angeles wildfires a year or so ago, you had the initial fires that damaged many buildings, but then you also had large-scale mud flows that occurred a few months later during the rainy season. And so this is sort of a common occurrence in areas that are prone to both wildfires as well as substantial rainfall. And so, we're seeing that electric utilities are understandably very focused on avoiding ignitions from transmission lines or other equipment. I think we're all familiar with PG&E and their role in the Camp Fire, which was California's deadliest wildfire. And so understandably, these utilities have been very focused on avoiding starting more fires. But what we haven't seen is much of a focus on understanding the vulnerability of electric utility assets to wildfires of any cause or to these post-fire debris flows. And so that's what we wanted to explore in this study. And so really we had these three main objectives or three main questions. So first we wanted to understand what is the current threat to power infrastructure in California from both wildfires and post-wildfire debris flows. So where do we see major threats from these climate hazards to these different assets? Second, how do we expect those threats to change in future climate scenarios? So we know there's a lot of uncertainty, but what can we say about how threat will change in different parts of the state or for different types of infrastructure? And then finally, we wanted to assess the vulnerability of different electric utilities. So moving beyond just threat to individual assets, but also trying to understand how does that translate to the different utility companies that are responsible for those assets? How does the vulnerability vary across different types of utilities, so on and so forth. Okay. So I'm not going to go super in depth on the methods here. I'm happy to share the paper, talk more about it at the end, but I do want to give you sort of an overview of the approach we took to solving this problem. And so essentially what we did was we took fine scale fire probability data. This was from Leroy Westerling's group out of UC Merced, hosted on the CalAdapt database. And so this shows the probability of a wildfire occurring in grid cells across California in both current scenarios as well as future climate scenarios. We also then looked at watershed level threat of post-fire debris flows, which were estimated previously by Mike Chester, my co-author, and one of his former postdocs. And again, we looked at the post-fire debris flow in watersheds both in a current scenario as well as in 4 future climate scenarios. And the climate scenarios we looked at a combination of 2 different representative concentration pathways. So we looked at RCP 4.5, which is sort of a middle of the road. You assume emissions start decreasing in the mid 21st century. And then we also looked at RCP 8.5, which is basically an upper bound. So you assume the emissions just continue to increase throughout the century. So we had those 2 concentration pathways, and then we also had 2 different climate models that we used. And so this was CAN-ESM, which is sort of an average future climate model for California, and then HADGEM, which is more of a warm, dry future, which again gets at sort of an upper bound for fire activity. And so these were not randomly selected. These are basically combinations that were recommended in California's 4th climate assessment as sort of reasonably bounding future conditions in California. And so with that, we hope to capture sort of a range of what these threats of both fire and post-fire debris flows could look like in the future. So we had these gridded probabilities and threat levels, and then we overlaid those with the location of transmission lines, substations, and power plants. So that gave us then the asset level fire threat for each of the types of assets, and then also the asset level post-fire debris flow threat. Okay, so jumping into the results here, and again, I'm happy to talk more about the methodology if there's interest at the end, but I don't want to go through all the details of post-fire debris flow modeling with this group unless there's sort of specific interest. So jumping into the results, we first looked at the current threat from both fire and post-fire debris flow to these different asset types. So starting on the left, this is essentially showing the probability of a wildfire occurring where each of those assets are located. So the lines are transmission lines, the circles are substations, and then the triangles are power plants. It's a little hard to distinguish them here. And then the darker red color is going to be a higher probability of wildfire occurring where those assets are located. So what we see is the highest fire probability occurs in the very northern mountainous part of the state, sort of up here, that's near like Mount Shasta and that area. There's a fairly elevated fire threat in like the Sierra Nevadas. And then also Southern California near LA and San Diego, we see a fairly high fire probability currently near those different electricity assets. When we look at post-fire debris flow threat, we see a slightly different results. I do want to point out, so here the threat, we have 7 different levels. Those are based on how likely a debris flow is. I'm not going to get into the details. It's basically based on how much rainfall would be needed to trigger a debris flow in those areas, given sort of fire probability, terrain, some other variables as well. And so what we see here, again, sort of the northern mountainous areas, those assets have the highest debris flow threats, but then also some places in sort of north of the Bay Area, in, again, sort of these northern Cascades, northern Sierra Nevada, and then a few hotspots down in Southern California near LA as well. So we also wanted to understand what future threat looked like. And so to do that, we looked at what the change in fire probability and the change in debris flow threat levels would be for each asset in each of the different future climate scenarios. And so you can see here in the top row, we have change in fire probability, where red indicates increased fire probability, blue indicates decreased fire probability. And then in the bottom row, we have change in post-fire debris flow threat levels, where this brown yellow color indicates an increase, and this sort of greenish turquoise color indicates a decrease. And so what I want to point out here is a couple of things. One, we do see some hotspots where we expect sort of the largest increase that are consistent, especially for fire, across the different scenarios. So these sort of northern Cascades, northern mountainous regions along here see a large increase in all of the scenarios. So that's likely somewhere where utilities with assets in those areas are going to see increased threat from wildfire in the future. And then there are also a couple of areas where we see consistent decreases in fire probability. And so that's primarily way down here in Southern California near San Diego. We see decreases across all of the scenarios. But I also want to point out there are a couple of places where we see sort of a range of different results. So for example, if we look around here, so sort of inland and north of LA, we see in some scenarios, so in the more average lower emission scenarios, we see a decrease in fire probability, whereas in the warmer and higher emission scenarios, we see an increase in fire probability. So for utilities who have assets in those areas, there's going to be a lot of uncertainty in what the fire threat to their assets will look like. When we look at post-fire debris flows, it's a little bit more varied across the scenarios. So there are a few places where we see consistent increases. So most of the northern part of the state, we see an increase in debris flow threat to assets across scenarios. Southern California, especially near LA and San Diego, depending on the scenario, could be a fairly substantial decrease in debris flow threat, or could be a fairly substantial increase. And so again, this is just to say that there's both large geospatial heterogeneity in terms of where the threats are expected to increase versus decrease, but there's also this large uncertainty in what that's going to look like in future scenarios. And so that's going to pose a real challenge for utilities who are trying to plan and dedicate resources to addressing these threats. So we also wanted to understand what this looked like for individual utilities. And so to look at that, we estimated what we're calling utility vulnerability, which was essentially just the percentage of assets located in high threat locations, both in terms of wildfire threat on the left, so these triangles, as well as in terms of post-fire debris flow threat, which we're showing with these circles. And so for fire threat, we are considering high threat anything with greater than 20% fire probability. And then for debris flow threat, we are considering high threat anything where a rainfall intensity that is more frequent than a 5-year return period would be considered a high threat of post-fire debris flow. And so I'm not going to go through sort of all of the details here. You can, look at the paper if you want to see exactly which utilities are most vulnerable. But one thing that we see here, so this is looking at transmission lines, and one thing that we see is that many of the utilities in this sort of top 5, top 10 here, most vulnerable in terms of both wildfire as well as post-fire debris flow threat, tend to be smaller publicly owned utilities. And we see the same thing when we look at power plants as well as when we look at substations. And so this poses a particular challenge because many of these utilities that are smaller, that are publicly owned, that are co-ops, they're municipalities, they tend to lack the in-house resources to do any sort of future climate modeling, to assess threat themselves. They're typically relying on state-level maps that show fire threat. Debris flow threat is sort of just being incorporated into some utility considerations. But these are utilities that don't really have the resources to, figure this out on their own. And yet they're the ones that appear to be most vulnerable to these threats. And so that's something that poses a bit of a challenge going forward. We also wanted to understand specifically how these threats translate to power generation, so which types of generators are most vulnerable. And so, as we know, California is looking to electrification as a means to achieve many of its decarbonization goals. But what we see here is that many of the types of generators that are most vulnerable to both wildfire as well as debris flow threat, sort of across both current and future scenarios, are these low carbon, sort of these clean, firm resources. So we have hydropower, nuclear, geothermal, wind, biomass. These are sort of the top most vulnerable types of generators. And so, as we're thinking about a decarbonized energy system moving forward, it's going to be really important that we are thinking through how these low carbon generators, how vulnerable they are to some of these climate hazards that we're starting to see more of. So just to wrap up here, so we have maybe a little time for questions or maybe at the end, but just some key takeaways. We've seen that current and future wildfire and post-fire debris flow risk vary quite a bit geographically across the state. So this isn't something where, it's sort of uniform. Given that heterogeneity, we're going to need very targeted mitigation efforts for these threats. And these mitigation efforts really need to take into consideration how the risk profiles will likely be changing in the future, and acknowledging that there's a lot of uncertainty in that. As I mentioned, we see that small publicly owned utilities are particularly vulnerable to both of these threats, and they tend to be the utilities that have the least resources to address them. So that's something that we would like to see, more support from the state, more support from other larger utilities sort of coming together to address some of these challenges. We also see these risks to clean, firm power generation that could challenge achieving some of the climate targets. And finally, I just want to highlight that addressing this problem, finding solutions, is really going to require cross-sectoral, multi-agency management approaches. As this, I've been talking about this problem in terms of electric utilities, but the threat of wildfires and post-fire debris flows certainly extends well beyond that. And so we would like to see coordination among electric utilities, water utilities, forest managers, everyone who is transportation agencies, everyone who's in this space who's impacted by these hazards. And that will likely be a more effective and more cost-effective way to mitigate these risks. So I will stop there. There's my email, and then I can put a link to the paper in the chat if anyone is interested. But otherwise, I'll stop sharing in case there are questions. I don't know if we have time or not, but yeah, I'll let you guys decide that.
Thank you so much, Nora. So I think we can leave the questions later after we finish with Anirudh's presentation. So I think we can go for that. Anirudh, it's your time.
Yes. Is this visible? All right, awesome.
Yes.
Yeah, thanks a lot for the invitation. I'm honored to give this talk. And I just want to um, start off by saying that I've really enjoyed the previous two talks. I've learned a lot, and I think perhaps somewhere my talk is perhaps touching upon a little bit of both what the previous speakers mentioned, but also a bit different. So I'm Anirudh Subramanyam. I'm an assistant professor at Penn State. I'm in very much in the operations research side. So my talk is going to be a little bit more on the method side. It's going to be less about modeling. By training, I'm an algorithms person, so you might see a little bit of computation in this talk. But I also don't want to kind of take up too much time by going into details, but I do want to kind of at least give you a flavor. And I should first of all start off by saying that all the work in this project was done by Taeyeon Kwon, who is so this was kind of his first paper, so to speak, his first PhD paper. And I also want to acknowledge funding by DOE for this work. So this talk is about capacity expansion planning. And for those of you who don't know, I'm going to guess most of you here are already familiar with the area or what the problem is about. But the idea is that you want to decide when to build or what to build, coal, natural gas, nuclear, um, um, storage, transmission, etc., in different parts of your region. Whether you're a system operator, so for example, if you're an RTO or an ISO, you might want to coordinate investments across regions. If you're a federal agency, you might want to, for example, understand how your grid evolves over the next few decades. And so this is kind of a very, very difficult problem because you need to kind of make these really, really long-term investments, which span many, many years and many decades. But this is made under deep uncertainty. So what makes this difficult is that these decisions have to be made before your futures are known. And this is particularly relevant now, for example, demand coming from things like data centers, which are kind of like the hot topic right now, extreme weather, which is increasing more and more, just like Nora mentioned in her talk. And we don't know what future extreme weather is going to look like, and of course, renewables. But at the end of the day, what keeps the ISO's job is not really cost. Well, I mean, of course, they want to minimize cost, but it's really to ensure reliability. And so, which just means that you want to be able to kind of capture the full detail of what can potentially happen in the next 50 years so that whatever investments you make now can kind of be able to provide reliable power supply over those decades. And so essentially, you want to kind of co-optimize long-term investments with short-term operations, all under uncertainty. And so this has been studied for many, many years and many, many decades. And so this talk is not going to be about the modeling. I'm not going to talk much about the modeling because this has been done by over many years and by many people who are on the call. But just to kind of give you a brief flavor, so this is typically done using something called stochastic optimization, which you may or may not be familiar with. Most of you are probably familiar with it. And the idea, the simplest version is called two-stage stochastic programming, which just means that you have kind of two stages. You have a long-term stage where you're going to decide capacity investment, which I denote with this variable X. And then once you make these investments, you can actually evaluate the cost of these investments by essentially doing some sort of dispatch or economic dispatch or a production costing. There are different names for it. And this is, again, it's itself some sort of optimization model. And this is typically done over a chronological set of future hours for a future time period. What makes this problem particularly challenging in the context of capacity expansion is that your uncertainties are multi-scale in nature. So you have long-term decadal uncertainties, which evolve over decades. Things like carbon policy, fuel prices, technology costs, but then you also have the short-term uncertainties like load, wind, and solar, which are driven by weather. I should point out, please don't get lost in the equations. The equations actually are not super important for the rest of this talk, but I think I only have like 3 other equations coming up, but they are really not super important for the talk itself. So what kind of makes this difficult from a modeling perspective? I mean, of course, from a modeling perspective, you want to have very, very fine resolution, both in your operations and in your uncertainty. So here's a picture of a typical production costing run, which is done with 8760 hours, which are the number of hours in a year. And you typically do these many number of dispatch decisions per generator. So if you have 1,000 plus generators in your system, that's 8,000 times 1,000. That's like 8 million decisions that you're making as part of your production costing, which is now embedded within the first stage model for capacity expansion. Now, of course, there are different ways of kind of modeling this. So, for example, a popular modeling technique is to only look at seasons and only to consider, for example, for the sake of optimization, you only consider 1 week in each season and maybe with 1 or 2 peak periods, right? And which can reduce the number of dispatch decisions. This is good, but in some sense, it is very manual and it is not clear how exactly do you pick that one representative week in each of your seasons. Another challenge is uncertainty resolution. What I mean by that is how many scenarios do you consider? How reliable is your investment decision? How many do you have to consider? This is particularly relevant now in the context of FERC Order 1920. If you're not familiar with it, I highly encourage you to look it up. FERC now requires all utilities and system operators to explicitly do scenario-based planning. And so the scenario-based plan, one possible attempt at kind of doing scenario-based planning is using scenario-based stochastic programming, whose equation I've shown. Again, you don't have to really stare at it, it's not important. But what kind of makes this challenging is for every additional scenario that you add into your problem, you are, depending on the scale of the system that you're solving, this is like on the order of, like I said, more than 1 million decisions that you have to put in and kind of solve together to kind of get the optimal capacity expansion. So there are different ways of solving this, which has, again, I'm not going to even attempt to kind of review the literature. The literature is long and vast. The most common way that many of you might be familiar with is to just model this problem in your favorite modeling language, and then throw it to a solver like Gurobi or Heis, which you may be familiar with, and just hope for the best and hope that it actually converges and hope that it actually gives you something. And many PhD student hours have been spent on trying to debug the outputs of these models. Another line of work is to look at scenario decomposition methods, which basically means you're going to look at each scenario individually and you're going to try to kind of get them to work together. In some sense, you're going to try to make sure that you're going to somehow adjust the objective function to make sure that they kind of reach consensus on one decision. This is also called progressive hedging. It is by far the most popular method, which is highly parallel, highly scalable, and you have off-the-shelf implementations for this method. Bender's decomposition is another one, which, unlike progressive hedging, which is scenario decomposition, Bender's decomposition is a stage decomposition method, which means it first solves the capacity expansion, which is stage 1. It then fixes it, solves the production costing, and it kind of iterates back and forth on those. Irrespective of which method you use, it's again unclear how many scenarios you want to use. And typically the way people do this is they do some sort of model sensitivity. And if you want to do any sort of model sensitivity on these kinds of models, it would require resolving the entire problem, which means you wait another 12 to 24 hours for every time you want to kind of understand the effect of one of these, of a new scenario that you might introduce. And so a lot of the majority of the work that we saw going into before we started working on this is that they kind of manually determine this model resolution, particularly in 2 aspects. One is the production costing operational resolution, and the second is the number of scenarios. If you choose a very low resolution model, you're obviously going to be able to solve it fast, and it's going to be tractable, and you won't have many bugs or numerical errors, but you cannot really trust how reliable the solution is. In contrast, if you have a very high resolution model, well, of course, the challenge is to solve it, but at least you have some confidence in your solution. Often these parameters are kind of chosen ad hoc without really some sort of statistical backing to them. And like I said, to kind of expert sensitivity would require resolving the entire problem. So this is kind of the problem that we set out to solve, and this is this is fresh off the press, this work. And so this is we call this AutoSCEP, which is automated surrogate-based capacity expansion planning, and this is on the archive, and it's going to appear in Electric Power Systems Research soon, and you're also welcome to take a look at the code. I'm not going to spend too much time on the method since I know we don't have a lot of time, but I'm just going to give you an overview of the method. And so the idea is that you're going to replace the expected cost in your two-stage stochastic programming model with essentially a neural surrogate. And this is the key step. So you're not essentially trying to learn a solution, you're just trying to estimate the expected cost. And this approach has also been recently called the Neural 2SP approach. And the way this works is as follows, and I'll kind of perhaps just stop after this slide and maybe jump directly to the results. This is the most important slide of the entire talk. So the way it works is you're going to sample some sort of, because it's a neural network model, you're going to do some sort of data generation, which means you're going to generate a bunch of potential investment decisions, and you're going to estimate its expected recourse cost. And there's a lot of work that goes behind actually generating this data. Once you have this data, you're essentially going to do a simple neural network fitting in PyTorch or your favorite environment, and then you're essentially going to embed that neural network into your mixed integer, into your optimization model. I'll probably skip the data generation part. I can come back if people are interested, and maybe just spend 10 seconds talking about how neural network, the embedding is done. So once you actually fit the neural network, once you actually train the neural network, embedding it can be done off the shelf by various packages that are available. And in the footnote, you can kind of see some of these packages, and I'll again just flash them here. These are very useful tools that you might want to explore yourself if you ever want to embed a neural network into an optimization model. So we kind of tested this on this test system from Europe. It's from a Norwegian group. We did not, like I said, we did not really spend any effort modeling. We wanted to take an existing open source model. There's an open source model which looks at capacity investment in Europe over 40 years. And there are essentially 1,000+ facilities to be considered for capacity investment. So this is a very, very large scale problem. So decisions are made every 5 years and for capacity investment. And in the second stage, we essentially do an economic dispatch at an hourly resolution. These are the uncertainties that were considered as part of, again, this is from the benchmark. This is not something that we have kind of handcrafted. They have electricity demand, generator availability, and water availability for hydro. This problem is extremely large. So if you just try to solve the problem without any uncertainty, just the base model, there's a linear program, by the way. So this is there's no unit commitment, there's no fancy stuff, there's no nodal capacity expansion. It takes about 2 hours of a barrier method with 16 CPUs. So it is extremely large. And so what we try to do is, and let me just jump straight to the results. And so what is shown in the red and the green are the performance of our method, and in PH 10 and PH 20 are the results of the benchmark, which is progressive hedging, which is the current state of the art for large scale compute. And this was all done on a high performance computing cluster. And kind of the highlights are I've kind of written it on the slide here. You essentially have to pay a one-time, because there's a neural network type of training approach. You have to kind of train your model. Training this model, you have to pay a one-time cost, just like you have to pay for like a large language model, right? You have to pay a one-time cost for training it, and there's about roughly 6 hours. And once you train it, solving the model is extremely fast, just like it is for ChatGPT. You just like, it's inference. And so this is similar in terms of inference. We get like within 1 minute, you can get a very good solution, which is roughly 8% in optimality gap compared to 11% using progressive hedging after 6 hours. And so we think the main benefit of this is to kind of do rapid evaluation of investment scenarios under different policy assumptions. We also kind of did some structural reliability to see whether these plans make sense. I can come back to that later if you're interested. But this was kind of the conclusion. We are currently exploring graph-based neural networks and richer operational models like nodal unit commitment. So it kind of makes things a bit interesting and also a bit more challenging. Here are the references, and I do want to say I'm open to collaboration. So if any of you are interested and want some help with computation, I'm more than happy to collaborate with you. Thank you so much. I'll stop sharing.
Thank you so much, Anirudh, and thank you all the panelists for our fantastic presentation. So now we are gonna open the floor for questions. Please feel free to unmute yourself or type the question in the chat.
Can I ask a question?
Yes,
Yeah,
of course. Yeah.
speaker prerogative. So for Ani, I'm curious how your solution quality compared to the Empire solution quality. Could you speak a little bit more about that?
Yeah, so we found that the investment patterns in transmission kind of matched the optimal solution. I should say, when I say the optimal solution, there is no optimal solution because it depends on how many scenarios you use to model uncertainty. But we consider optimal to be 100 scenarios. And so you can take that with a grain of salt. But compared to the model with 100 scenarios, which I think took like 2 weeks to solve on our compute cluster, we found that the transmission investments were kind of matching in terms of the trajectories of investment over time. The generation and storage investments were there was a little bit of discrepancy, but in terms of kind of the overall patterns, where you kind of have this rapid investment in transmission, which you kind of stay idle for the rest of the next 30 years. So you have rapid investment for 20 years, and then it stays idle for the next 30 years is kind of what we found. Was kind of being replicated by this neural network model, which we do think is important to build trust, because you want to make sure that like whatever this neural network is giving you is something that would make sense in reality. And personally, I would give it a score of 60 on 100, not 100 on 100. So this is really more of a computational method, but this is still something that we're investigating, how to kind of go from 60 on 100 to 100 on 100. So, but that's still up in the air.
Thanks.
Yeah, that was great. I had a question, but Nora answered it with her paper, so that was awesome, but very cool to see. Yeah. Does anybody else have any other? Oh yeah, you go.
I'm curious about that because, like, the point that you raised in the chat about clean firm, and I guess for the geothermal results, which I'm especially interested in, surprise, surprise, this is what we work on a lot of the time here. If we're, would your results suggest that geothermal planning or geothermal companies should be looking at a particular region and should be looking to avoid particular regions? Let's say in the Western US, if they had a choice between like California and maybe Utah or Nevada.
Yeah, that's a good question. And it's not something we explicitly looked at in the paper, but I guess my short answer is yes and no at the same time. In that I think what this paper shows is that for both planning and operation of current assets, I think, there's a need to look at the climate hazards. So you should be looking at fire risk, you should be looking at debris flow risk, you should probably also be looking at other climate hazards, you should be looking at flood risk, so on and so forth. But in terms of yeah, I guess we looked specifically, at existing assets, but you could certainly take, the grid level fire probabilities and the watershed level debris flow probabilities, and you could work that into, a more future, whether it's a capacity expansion model or it's, whatever else, but for future planning, I think we would argue that building in some of those, future expected threats would be a good idea at this point. Yeah.
But it's interesting that the main reason is small assets versus big assets, and that basically smaller assets are maybe more resilient to climate than right? But then because there's economies of scale with the big assets and all these values to centralize. stuff. So it's really interesting to see the trade-off between kind of like large centralized versus small decentralized in different contexts of climate or energy or economics. So,
Yeah, and I guess maybe just I would clarify one point on that. I think it's less small versus big
okay.
per se, more I guess if it's sort of, concentrated, whether that sort of one large asset is sort of inherently concentrated in one location versus more distributed, but yeah, sort of whether you're yeah, if for example the utilities that had, not that many assets, but they were all in high threat areas,
Yeah.
that's a lot more vulnerable than the utilities that have a bunch of assets that are really spread out, or not that many, but that are spread out. Yeah. So I think it's more about sort of the distributed across different types of areas versus sort of grouped or single assets. Yeah.
It's hard because it's a multi-objective problem, because you want to maximize like the location of the good geothermal, but you also don't want it to get messed up. So
Right.
it's really cool. Really
Yeah.
cool. Good work for multi-objective people.
Yeah.
Thanks. Awesome. Wow.
Yeah, I guess we should be overlaying geothermal potential maps with your
Yeah.
maps, Nora. Yeah.
Yeah, I think that would be great.
That's what I'm thinking. Yeah, that's cool. And I really loved your missing market work, Emil. That was really cool.
Thank you.
We had talked about that at the conference, but I didn't realize that you had all these papers on it. So this is exactly what this is for.
Mhm.
Great. Nice. Awesome.
Yeah, and there's good work coming out of from colleagues as well on this, and we're more and more looking at storage as well, and looking forward to talking more about these things as well.
Yeah.
As we get more results and get to understand the problem better. Yeah.
Yeah.
Mm.
Yeah, I'm curious, like if that's also like a pro for something like geothermal, if it works better in incomplete markets compared
Mm.
to like variable renewables and storage.
Um, yeah, not necessarily. Actually, clean firm. I think one of our particular concerns is that clean firm might be disadvantaged in electricity markets where you don't have, yeah, in electricity markets in general. And I think we see that historically too, with how nuclear developers haven't had an easy time finding off-takers for contracts.
Yeah.
And that's for a lot of reasons, but if I guess we contrast that with cases where nuclear has been built before, and usually that has required some good risk hedging mechanisms. And the UK is showing that, for example, although, they're also paying the cost of nuclear is very expensive when you have forgotten how to do it. But yeah, these clean firm is on it's like on the one hand, it's better able to pass on risk premium to consumers because it's very valuable. But on the other hand, it's also very much exposed to market risks. If you make a lot of your revenues during rare periods when there's very high electricity prices,
Yeah.
your profits are very risky. So there's kind of um, renewables and clean firm are both vulnerable to this for different reasons. To like wrap up this very long answer.
Yeah. That's yeah. So cool. Yeah, I feel like I want the same plot that Nora had, except just for your problem. You know what I mean? Like each technology and the vulnerability to incomplete
Mhm.
markets.
Mhm.
That would be really
Okay.
cool.
I'll take that. I'll take that back to the lab. Thanks, Jackie.
Nice. Awesome. Thanks, folks. Any other dingling questions? Last questions? Nice. This was awesome.